Hello friends, welcome to the second part of the video of fluid mechanics. In this video we are going to discuss the rest of the topic which we have left in part 1 of the video. First of all we will start with fluid dynamics. Fluid dynamics is the study of the fluid flow with the forces causing the motion. Okay, in this the dynamic behavior of the fluid flow is analyzed using Newton's second law of motion, that is F equals to ma. Okay, uh, first of all let's take a look of Euler's equation of motion, that is force of gravity plus pressure force equals to ma, and using some integration we will come to the Bernoulli's equation of motion. From this Euler's equation of motion, this Bernoulli equation of motion is P upon rho plus gz plus v square by 2. We know the meaning of respective term. P is the pressure, rho is the density, g is the acceleration due to gravity, h is the elevation above the datum of the water or the liquid, and v is the velocity of the flow. This is equals to constant. Now this Bernoulli equation of motion is applicable for along the streamline, for steady flow, for incompressible flow, and for effect of viscosity or friction when it is neglected. Okay, then only we can apply the Bernoulli's equation of motion. Now in terms of energy per unit length or energy head, we write this equation as P upon gamma plus z plus v square by 2g equals to constant. Usually in the calculation we use this expression for the Bernoulli's equation. Now the kinetic energy correction factor. Kinetic energy correction factor is alpha. It is equals to actual kinetic energy upon kinetic energy calculated using average velocity. Okay, how we will find out average velocity? Using this formula, line integral of v dot dA, vdA upon total area. Okay, and how we will find out kinetic energy? Using integration of v cube dA upon a v average cube. V average we have determined from here. We know the area, and we will integrate the velocity with respect to area. Okay, now alpha, value of alpha equals to 2 for circular pipe. We have to memorize this value. Next is the application of Bernoulli's equation. First one is venturimeter. Venturimeter is you must be very much familiar with venturimeter. This is the venturimeter. We have the bend in the pipe here. Okay, this is the contraction of the area and then elongation. This is rapid contraction and this is gradual elongation in the pipe. Okay, and we find out the difference of the pressure between these 2 points, point 1 and point 2, and this is the variation in the head between these 2 points. Now if we have to determine the Q, that is the discharge through this pipe, then we will apply this formula for venturimeter. This is CD A1 A2 upon under root A1 square minus A2 square under root 2 GH. A1 is the area at this point, area of cross section of the pipe. A2 is the area of cross section of the pipe at 2, that is the contracted section. CD is the coefficient of discharge, having different values for different cases. Now if we account for the losses, then value of CD equals to under root 1 minus HL upon H. HL is the total head loss in the pipe during this process of contraction or expansion. Okay. Now for inclined venturimeter like this, if you are having the venturimeter like this, now in this case we are having Q equal to CD A1 A2 upon under root A1 square minus A2 square root 2G G2 by G1 minus 1 into X. Okay, where G2 usually we provide a differential manometer here. Okay, and we fill it by some liquid. This liquid is having specific gravity of G2, and the liquid which are flowing, that is having the specific gravity of G1. Okay, so this is G2 by G1 minus X. X is this difference in the elevation between these 2 points in the differential manometer. Okay, normally dia of throat is half of diameter of the pipe. Okay, this is diameter of pipe, this is diameter of throat. Okay, the angle of convergence usually we take 22 degree. This angle is to 22 degree, and angle of divergence is 6 degree. That is gradual expansion to prevent the flow separation. Okay. Next is the orifice meter to find out the discharge through a pipe. In the orifice meter, you can see here that section is created through which the flow is taking place. This is the vena contracta, the section of vena contracta. Okay. Now A1 is the cross section area up to at this point. A2 is the cross section area after vena contracta. At the point of vena contracta, we are having A0. Okay. Now Q having the same formula, CD A1 A2 upon under root A1 minus A2 whole square into root 2 GH. Okay, the same H is determined as in the Venturi meter. Now value of CD is usually taken at H.6. Okay. Next is nozzle meter. This is a nozzle attached in the pipeline, and through this we are having the area of nozzle as A0. Then we can put this value here like CD A0 A2, sorry, A1 A0. This is A0. CD A1 A0 upon under root A1 square minus A0 square root 2 GS. Here CD is taken as 0.98. Okay. Now few are the velocity measurement devices like pitot tube and Prandtl tube. Pitot tube, you must be familiar with it. V equal to CV root 2 GH. Here we provide a tube like this, okay, in the pipeline, and we measure the difference in the elevation in this tube between point 1 and point 2. Point 2 is at the center and point 1 is at the surface of the pipe. Okay. Now Prandtl tube. There is one disadvantage in the pitot tube is that when there is a bend or turbulent flow at that moment, pitot tube becomes unuseful. Okay, there we cannot find out the velocity using pitot tube, but in the Prandtl tube we can form a laminar flow in this tube. Okay, and this velocity can be determined using the same formula, V equal to CV root 2 GH. Here we are providing a tube here like this, and in the tube, inside this tube, we are having another tube. Okay, and we find out the elevation in this tube. This is the difference in the elevation between outer tube and inner tube. This is the H equals to VA square upon 2G. Okay. Next topic is weir and notchage. What is a weir? A concrete or masonry structure placed in an open channel over which the flow occurs. Notches, a device in the form of metallic plate placed in a small channel for discharge measurement. Okay, weir and notches we provide along any river or any water body, and a flowing water body, and we measure the discharge through it. First case is the rectangular weir. Rectangular weir, we can see it here like this. This is the cross section of the rectangular weir whose width is L. Okay, and this is the height of the weir. Here there is a gapped portion. It is called nappe region, where some swirling occurs of the water. Now this is the datum. The height of this top of the weir above the below the top of the line of flow of the water is H, and V is the approach velocity. Now Q is equals to 2 by 3 CD root 2 GL H plus HA raised to the power 3 by 2 minus HA raised to the power 3 by 2. Now HA equal to VA square upon 2G, where VA is the approach velocity. If approach velocity is neglected, then Q equal to 2 by 3 CD root 2G L H raised to the power 3 by 2. Now for triangular weir or V notch, this is the triangular weir. Okay, this is the theta angle and height is H. Here we are having the formula of discharge as 8 by 15 CD root 2G tan theta by 2 H raised to the power 5 by 2. CD is 0.5 in this case. Okay, now advantages of triangular weir. The variation of coefficient of discharge is less. For a particular discharge, depth of the flow will be greater, and efficient for low discharge also. As we can see here that for low discharge also we can make a proper calculation here. Now trapezoidal weir, it is the sum of triangular and rectangular weir. You can see the triangular portion here and the rectangular portion, and the discharge is sum of both of those formula. If we put the value of tan theta by 2 here as 1 by 4, then this triangular weir will become a Cipolliti weir. Okay, CD value is 0.62. Next is broad crested weir. This is the broad crested weir. Total energy line, this is the flow line, and this is the datum assumed at the top of broad crested weir. Okay, now this is the height of the flow above the weir. Okay, and Q is equals to 1.704 CD L H plus HA raised to the power 3 by 2, where CD is 0.85 to 1. In the case of proportional weir, Q is directly proportional to H. Usually we have seen in other cases like Q was directly proportional to H raised to the power 3 by 2, or in the triangular weir it was proportional to H raised to the power 5 by 2. But in the proportional weir, we are having Q is directly proportional to H. Here we write the value of discharge equals to CD L root 2G A H minus A by 3. This is the A. This is the hyperbolic curve. Okay, CD equals to 0.5 to 0.6 to 0.65. Now the spillway is the case where nappe is removed and a weir is formed. Here the flow is just attached to the surface of this weir. Okay, no nappe region formed in this. Q equal to 2 by 3 CD root 2G L H raised to the power 3 by 2. Same in the case of rectangular weir. Now the percentage error in the weir, dq by q into 100 equals to n times dh by h into 100, where n is the, you know, the power, this power, that is 3 by 2, 5 by 2, etc. Now we can find out between 2 points. If we find out the error, then we can write down expression like this: q2 minus q1 upon q1 into 100, h2 raised to the power n minus h1 raised to the power n upon h1 raised to the power n into 100. Next topic is laminar flow in the pipe. The flow in which one layer sliding over the another layer, since there is no mixing between different layer, hence shear is entirely due to viscosity. Okay, when two layers slide past each other, okay, then this process is called laminar flow. Okay, now Reynolds number equal to Vd upon nu. This is kinematic viscosity, D is the dia of the pipe, and V is the velocity of the liquid flowing. Now for laminar flow, this Reynolds value is less than 2000 in circular pipe. For transitional flow between 2000 to 4000, and for turbulent greater than 4000. Now in circular pipe, the shear stress equals to minus dp by ds r by 2. This r is the this radius of the pipe, up to which we have to determine the shear stress. Now dp by ds is pressure gradient from 0.1 to 0.2. Okay, and this formula is valid for both laminar and turbulent flow. Now value of velocity in circular pipe in the laminar flow is 1 upon 4u minus dp by dx r square minus r square, where capital R is the radius of the pipe and r is the this length from the center of the pipe to some extent at which we have to find out the velocity. Okay, now u equal to u max 1 minus r square upon r square. Q is the pi upon 8 mu minus dp by dx r raised to the 4. This mu is the coefficient of viscosity, dynamic coefficient of viscosity. Now point where average velocity equal to local velocity is r equal to 0.707 r in the case of circular pipe. Okay, now laminar flow between parallel plates is dp by dx d tau by dy. This formula is used in laminar flow between parallel pipe. Okay, the difference in the pressure between 2 points equal to in the direction of x is the shear stress, variation of shear stress in the y direction. Okay, now tau we can put it like the value of tau as mu du by dy, and dp by dx will become mu d square y upon dy square. Now determining the value of u in this between parallel plate is 1 upon 2 mu minus dp by dx by minus y square. We can see here like b is the width, total width, and y is the width from the this, from one surface towards the point where we have to find out the velocity. Okay, now q is equals to 1 upon 12 mu minus dp by dx b cube. This is the discharge value, and u max equal to 1 upon 8 mu minus dp by dx b square. Average velocity is 2 by 3 of maximum velocity. Now the pumping power required for the flow, power equal to P1 minus P2 into Q. Okay, difference in pressure into discharge. This is valid for steady and uniform forces, that is kinetic energy will not change. In those cases only we can apply the formula of this power. Now head loss in the pipe, in the case of laminar flow, in circular pipe, HL equals to 32 mu average into L upon gamma d square. Gamma is the unit weight, d is the dia of the pipe, V average is the average velocity, L is the length of the pipe, and mu is the dynamic viscosity. Now HL equals to 128 mu QL upon pi r d raised power. We just have kept the value of V as Q upon area here, and this formula is called Hazen-Pasolini equation. Okay, HL is inversely proportional to d raised to power 4. We have to memorize it. HL is inversely proportional to d raised to the power 4. Since discharge is constant, velocity is not constant, so we cannot regard it as HL is inversely proportional to d raised to d. Now Darcy-Weisbach equation is HL equal to FLV square upon 2GD. Okay, head loss is like this, and head loss here we are having the friction factor F. Okay, now if coefficient of friction we have to determine from friction factor, then coefficient of friction is F upon 4. Okay, the value of F is 64 upon RE. RE is the Reynolds number. Now head loss in the parallel plate is HL equals to 12 mu QL upon gamma B square. B is the width between the two plates. Okay, now HL is inversely proportional to B cube. Here we can see that HL is inversely proportional to B cube. Now kinetic energy correction factor alpha for laminar flow in the circular pipe, alpha equals to 2. For laminar flow in parallel plate, alpha equal to 1.543. For turbulent flow in pipe, alpha equal to 4 by 3. Momentum correction factor beta for laminar flow through pipe, beta equal to 4 by 3. For turbulent flow through pipe, beta equal to 1.015. For laminar flow between parallel plate, beta equal to 1.2. This is a simple question asked directly in the examination in the for the objective purpose. Now settling of the particle through an infinite medium. Here this terminal velocity through which this particle falls down in this medium. Here we can see here that weight is acting downward, drag force is acting upward, and buoyant force is also acting upward. So drag force formula is Fd equal to half CD rho AV square. A is this area, cross sectional area in the plan. Rho is the density of this liquid, V is the velocity of the flow, and CD is the drag coefficient. Okay, now W is volume into unit weight. Okay, so terminal velocity here Vt square equal to 4 by 3 gamma s minus gamma w d upon CD rho. For laminar condition we have the value of CD equal to 24 upon Re. So our terminal velocity formula will change as Gs minus 1 gamma w d square upon 18 mu. Okay, next is our turbulent flow. Turbulent flow, the fluid parameter starts varying with space and time in turbulent flow. Here shear stress equal to viscous shear stress plus turbulent. Okay, viscous we have the formula of mu du by dy, but for turbulent we are not having the formula. So here the von Karman and Prandtl, they have given the formula of turbulent shear stress as rho u dash v dash. Value of u or v we keep here as 0.4 y du upon dy. So this formula become rho 0.4 y square du upon dy whole square. Here 0.4 y is represented by L equals to ky equal to 0.4 y, where this 0.4 is the Karman constant, von Karman constant. Okay, now hydrodynamically smooth and rough surface, we can see here this is the surface. Okay, this is the total thickness of laminar sublayer, or here is the eddies formed at this point, and average height of roughness projection. This is the roughness in the pipe. Okay, we denote it by K, average height of roughness projection. So here we can see the formula of this thickness of laminar sublayer equal to 11.6 nu upon u star. Nu is the kinematic coefficient of viscosity and u star is under root tau by mu. Okay, when this mu, that is coefficient of viscosity, dynamic coefficient of viscosity, increases, then this thickness of laminar sublayer also increases. But if the velocity increases, then this thickness of laminar sublayer decreases. There are few values we have to memorize here, like for the k upon lambda dash, k is the average height of roughness projection, k upon lambda dash less than 0.25 for hydrodynamically smooth section of the pipe. For transitional transition we are having 0.25 to 6, and for greater than 6 we are having hydrodynamically rough pipe. Next is the velocity distribution in circular pipe for turbulent flow. For smooth pipe there are few formulas here we have to memorize here. For smooth pipe, u minus u average upon u star equal to 5.75 log of y by r plus 3.75, u upon u max equal to y by r 1 by 7. This is called 1 by 7 power law. For rough pipe, u minus u average upon u star equal to 5.75 log base 10 y by r plus 3.75, u max minus u average upon u star equal to 3.7. Losses in the turbulent flow in circular pipe equal to FLV square upon 2GD. This is normal frictional loss. And for smooth pipe, F equals to 0.316 RE raised to the power 1 by 4 for RE ranging from 400 to 10 raised to power 5. F equal to 0.0032 plus 0.221 upon RE raised to power 0.237. RE ranging from 10 raised to power 5 to 10 raised to power 7. This is Nicoratse formula. And for rough pipe, this was case of smooth pipe. For rough pipe, 1 upon root f 2 log base 10 r by k plus 1.74, where k is artificial sand grain roughness of the pipe. Okay, now k equal to k naught alpha t. Okay, so this is the value of k which we have kept here. Okay, and to find out f we use the value of k. Next topic is boundary layer theory. We can see the boundary. This is the object or the plate kind of object inserted in the liquid and against the flow. If the velocity of flow is v naught, and then we can see here a boundary layer is formed like this. This portion up to the transition is laminar layer. After this we are having transition and the turbulent boundary layer after transition. Okay, in the turbulent boundary layer we have the laminar sublayer as we have seen it earlier. Okay, now the front edge is called leading edge and the final edge, that is exit edge, is called trailing edge. Here RE, that is Reynolds number, is v naught x upon nu, where v naught is the approach velocity v naught and x is the distance from the leading edge and nu is the kinematic viscosity. There are few boundary layer condition we have to memorize. Few are the essential condition, like at x equals to 0 in the starting of this boundary layer we are having delta equals to 0, thickness of this boundary layer is 0. At y equals to 0, v equals to 0. Okay, velocity here is 0. Now at y equal to delta, that is at this point, v equal to v naught, that is free stream velocity. At y equals to delta, du upon dy equal to the rate of change of velocity equals to 0. There are few desirable condition also. At y equal to delta, d square y upon dy square equals to 0. Now the change of the boundary layer from laminar to turbulent is affected by, what are the factors affecting the change of boundary layer from laminar to turbulent are roughness of the plate, intensity and scale of the turbulence, pressure gradient and plate curvature. Plate curvature like this. Okay, this is the plate curvature and this is the boundary layer formed. Pressure gradient, you can see here that at the starting point, if we are having the pressure at P1, at the transition we are having P2 and P3 in the last, we are having P1 is greater than P2 in this region. If that means the negative pressure gradient is formed and this causes the acceleration in the starting phase. But in the turbulent phase of width of length x2, we are having positive pressure gradient and this causes the retardation of the flow. Okay, now at the x critical distance, that is where the transition occurs, we are having the value of Reynolds number, that is v naught x cr upon nu is equals to 5 into 10 raised to the power 5. Okay, there are few boundary layer thicknesses. Nominal boundary layer thickness, we must have seen it earlier. Distance from boundary in which velocity reaches 99% of the free stream velocity. Now displacement thickness is distance by which boundary should be shifted in order to compensate the reduction in the mass flow rate on account of boundary layer formation. Like we can see here, this is the pipe, okay, and this is the boundary layer formed. The velocity here was v naught, so we are having the mass flow rate of rho pi d square by 4 into v naught. Here we are having the velocity as v. Okay, if we have to change it into a constant thickness of the velocity, then we take this displacement thickness into consideration. This is the delta star, and now we are having this velocity as v. Now this velocity is kept here like this. Okay, so distribution will be linear. Now the mass flow rate will changes to rho pi d minus 2 star 2 delta star square upon 4 into v. Okay, so these two mass flow rate will be same. The displacement thickness, the formula is delta star equals to integration of 1 minus u upon v naught dy from 0 to delta. Okay, momentum thickness is theta. Theta equals to integration of 0 to delta u upon v naught 1 minus u upon v naught into dy. Energy thickness is integration from 0 to delta u upon v naught 1 minus u square upon v naught square into dy. Now shape factor for boundary layer is delta star, that is displacement thickness upon momentum thickness. We must remember that displacement thickness has the greatest value, then the energy thickness, and least is the value of the momentum thickness. Now u upon v naught equal to y upon delta raised to the power m 1 upon m, sorry. So usually this value is this expression for velocity is provided in the questions. Next is the von Karman equation. Von Karman momentum integral equation, tau upon rho v naught d theta by dx. Okay, here tau w is the boundary shear stress, v naught is the free stream velocity, rho is the density of the water or the liquid, and theta is the momentum thickness, and x is the distance from leading edge. Okay, this is the von Karman momentum integral equation. This is valid for STD, two-dimensional compressible flow. Okay, next is the friction drag coefficient value. This is the local drag coefficient, and this is average drag coefficient. In the local drag coefficient, we are having value of tau x upon rho v naught square by 2. In the average drag coefficient, we are having the value of tau average upon rho v naught square upon 2. Next topic is drag and lift. This is the formula of drag, half CD rho AV square, and this is the formula of lift, half CL rho AV square. Okay, area is the projected area perpendicular to the direction of the flow. Like if we are having a body flowing like this, then the area seen from this direction is this cross sectional area is the projected area perpendicular to the direction of the flow. Rho is the density of the air or liquid flowing. Okay, velocity of the flow is v, and CD is the coefficient of drag. Similarly, in the case of lift, we are having area as the plan area, like this area if we see from the top. Okay, this is the plan area. Now the component of the force acting on the surface of the body in the direction of the flow of the stream is drag force, and the component of the force acting on the surface of the body in perpendicular direction to the direction of the flow of a stream is lift force, that is upward flow. This is lift force and this is drag force. Okay, now frictional drag. This is the frictional drag along the surface of the body and this is the form drag. Form drag is like this. This is the eddy is formed here. Take the form drag. Okay, at very small Reynolds number, total drag equal to deformation drag. Deformation drag is the sum of pressure drag and frictional drag. At larger Reynolds number, separation of boundary layer start taking place. Thus, at higher Reynolds value, total drag equal to frictional drag plus form drag. Form drag was due to separation of boundary layer. Okay, now the boundary layer separation we can see here. This is the boundary layer. Okay, and up to this point we were having the attached flow. Attached flow is moving like this. up to this point. Here we are having the value of du upon dy at y equals to 0 is greater than 0. Du upon dy at y equals to 0 at the verge of separation, and at when the flow is already separated, then we are having the du upon dy at y equals to 0 less than 0. Okay, this is the separated boundary layer, we can see it here. Up to this point, this is the separation region. We are having the negative value of rate of change of velocity with respect to y, and after this boundary layer we are having the same case as we are having here. Here we are having v naught value, this is the free stream velocity, and this is also the free stream velocity. Okay, now drag on the sphere. This is the basic formula for Reynolds number less than 0.2. Drag force is 3 pi mu dv, where d is the dia of the sphere, v is the terminal velocity, mu is the dynamic coefficient of viscosity, cd value is 24 upon re. Next topic in the fluid mechanics is modal analysis. Modal analysis, we are having different types: a geometrically similar model and distorted model, like river, harbor. Okay, types of similarity there are: geometric similarity in the length, width, etc. For kinematic similarity, we are having similarity in the velocity, acceleration, discharge. Dynamic similarity is for forces and power, etc. Now for kinematic similarity, geometric similarity has to exist, that is a must condition, and for dynamic similarity, geometric and kinematic both similarity has to exist, that is a must condition. Now important dimensionless number which we have to memorize. Reynolds number equal to inertial force upon viscous force. Inertial force we are having dimension as rho L square V square. Viscous force we are having dimension as mu V L. So the formula will become rho V L upon mu. Fluid number is under root of inertial force upon gravity force. We are getting the formula as V upon root GL. Euler number under root inertial force upon pressure force, getting the formula as V upon under root P upon rho. Weber number is under root of inertial force upon surface tension, getting the formula as V upon under root sigma upon rho L. Sigma is the surface tension. Okay, and match number is under root of inertial force upon elastic force, or we can say compression force. This is having the formula as V upon under root K by rho, where K is the compressibility, that is the bulk modulus of elasticity, and rho is the density. Okay, so this under root K by rho for rigid material becomes C, that is the velocity of sound. Okay, if the velocity of flow is greater than velocity of sound, V is greater than C, then this is the supersonic condition, V is less than C is the subsonic, and V equal to 0 is sonic condition, V is much greater than C, the condition of hypersonic. Now the model laws, we are having the Reynolds model law. First one is the Reynolds model law, used when the dominant force is viscous force. Here Reynolds number is equated for prototype and the model. Okay, and we get the value as rho r Lr Vr upon mu r equals to 1. This is used for the flow around completely submerged object. Okay, next is the fluid law. Fluid law is when gravity force is dominant, Vr upon under root Gr Lr equals to 1. Here we can see that Vr, that is velocity ratio, is directly proportional to the under root of length ratio. Applicable for the free surface flow. Usually this is very important for the free surface flow, like in the case of spillway, open channel flow, weirs, hydraulic jump, notchage, etc. Next is the Euler's law. When pressure force is dominant, Vr upon under root Pr upon rho r equals to 1. This is applicable for the pipe flow under very high pressure due to sudden closure of the wall. Okay, like in the case of water hammer pressure. Next is the Weber model law. When surface tension is dominant, Vr upon under root sigma r upon rho r Lr equals to 1, applicable in the capillary rise through narrow passage, like flow in the blood, flow of blood in the veins, seepage through soils, etc. Now match law, when compressibility force is dominant, Vr upon under root Kr rho r equals to 1. This is applicable in the case of aerodynamic testing, such as launching of the missile, rocket, torpedoes, etc. Next topic and the last topic in our syllabus is pipe flow. Most of the pipe are having the turbulent flow. Okay, in the pipe flow, in the start we consider the losses in the pipe.
Major loss is due to the frictional loss, that is FLV square upon 2 GD. We have seen it earlier also. Minor losses is due to two reasons, due to sudden expansion, like in the case of the entry of the pipe into the reservoir, like this. V1 is the velocity in the pipe and V2 when it enters in the reservoir. Then the head loss is V1 minus V2 whole square upon 2Z. This is equals to K V square upon 2Z. Value of K, we can usually have the value of K equals to 1. Okay, in the case of entry of the pipe in the reservoir. Now velocity of the smaller dia pipe is kept here, kv square upon 2z. Now due to sudden contraction, we are having the formula of head loss equal to k v2 square upon 2g, where k equals to 0.5. okay, like in the case of entry of the pipe, like this. v1 and v2, we are keeping the value of v2, that is velocity when it enters in the pipe. Next is the pipe connection. Pipe connection are of two type, either parallel or series connection. In the parallel connection, we are having the head loss same for all these cases 1, 2 and 3. Q, value of discharge, is the sum of 1, 2, 3. Very much easier to understand. In the series connection, we are having head loss is HL1, HL2, HL3, sum of these three. Head loss occurring in 1, 2 and 3. And Q is the same in 1, 2 and 3. Now the equivalent pipe is the pipe which can replace existing compound pipe while carrying the same discharge. Like in this case, if we want to replace this series connection, then we will apply some equivalent pipe having the head loss as sum of HL1, HL2 and HL3. Okay, and the Q will be same for it. Now the power transmission through pipe, we can see here that this is the reservoir, this is the total head, and head available is H minus HL, that is total head minus head loss. Then if we neglect the minor losses, then the head available will become H minus HF, that is head loss due to friction only. Okay, then the power available will be gamma H minus HF, and the efficiency will become power available upon power which was earlier possessed by this liquid. Then this efficiency become gamma q H minus HF upon gamma q H into 100. We can write it down like this also, H minus HF upon H into 100. For maximum efficiency, value of head loss due to friction has to be total head available upon 3, and the maximum efficiency will become 66.67%. The last topic in the fluid mechanics now is water hammer pressure. For the rapid closure condition, we are having the time of closure. If we can see here that this is the reservoir and this is the pipe getting out, and the liquid is flowing with the velocity v before the closure, and as soon as the valve is closed, okay, then a wave will develop here having the velocity as c. Okay, now this is the length of the pipe, and we call this closure as rapid closure if this time of closure, that is this sudden closure, is less than 2L upon C. This is the length and C is the wave velocity. Now for rigid pipe, this value of C is under root K upon rho. K is the bulk modulus of elasticity of this liquid and rho is the density of this liquid. Now for flexible pipe, under root K by rho upon 1 plus D by T upon K by E raised to the power 1 by 2. D is the dia of this pipe, T is the thickness of the pipe, K is the bulk modulus, and E is the modulus of elasticity. Okay, and water hammer pressure is pH equals to rho C V1, rho C V, that is the velocity flowing into it, C is the wave velocity, and rho is the density of the liquid. Okay, so here we are finishing up with the fluid mechanics portion. For any doubt, you can mail me at windsofchange2020@gmail.com. If you are having any query here, you can write in the comment. If you like this video, click on the like button, share this video as much as possible. Thank you.